Thermochemistry, heat and work. Thermo meaning heat.
So let's look at how ice is made. Now you want some ice cubes. We put water into the freezer. The freezer is very cold, less than 0 degrees. And we think, a lot of people have the conception that the cold from the freezer goes into the water and then we get ice cubes. Well, is that correct? No, that is not correct. Cold does not travel. There's no really such thing as cold traveling. What we really get is the heat leaves the water and goes to a colder place, which is the freezer. So the water is warmer, the freezer is colder, and the heat will leave. It is not the cold going into. Heat will leave. Heat travels from high to low. So heat will leave the water to go to the cooler surrounding. Now, let's say you have those ice cubes and we want to have a delicious cola drink. And we fill it with cola, or as people in Michigan say, pop. That's actually what I call my dad. I call him Pop. Anyway, now the heat from the cola goes into the ice cubes. The cola is hotter, has more heat, so it will go into the ice cubes. And what will happen is the ice cubes will get smaller. The heat from the cola goes into the ice cubes. The ice cubes will absorb some of that heat, making those ice cubes smaller. The cola gets colder. Now you have your delicious drink, and yum, cold pop, as people in Michigan say. Now, in another example, let's say it's January, and you have your fireplace, and you have your picture over your fireplace of your favorite person, and you have your fireplace going. It's nice and toasty inside. And then you open up the door, and outside it's freezing cold, as in January does get. We have the snowman here. And then what happens? Your mom yells at you and says, "Close the door, you're letting all the cold in." Well, we know that cold doesn't go in, heat will leave. It might seem colder where you're standing by the door. That's because heat is leaving. Heat will go from high to low. Heat leaves. And conversely, let's say it's the middle of July, you got your fan going or your fancy schmancy air conditioning, and we have right by the favorite person picture, and we open up the door, it's July, and we have hot stuff outside, hot weather. Even the sun is sweating. Poor sun. It's hot in the middle of July. And your mom yelled at you, "Are you letting the cold out? Close the door. All the air conditioning is getting out." Well, that is wrong. The heat comes in from the outside.
Now heat, notified by the symbol Q, is what we're looking at in this chapter. Now heat will always flow from a warmer object to a cooler object. So heat flows from warm to cold. It has more energy. So we know that things with higher energy go towards something with lower energy. Whether it be potential energy, a ball on a hill, that will go to something that is on lower energy. And the same thing can be said of heat. Heat has more energy. Something with heat has a lot more energy. Molecules are moving around a lot faster, a lot quicker than something that has lower energy. The molecules are moving around much less quickly, slower. That energy will be transferred. It will go from high to low. You always will go from energy of high to low, heat, high to cold.
Okay, let's look at system and surroundings. They're very important to know the difference because you can get into big trouble if you can't find the difference out. Now let's say we have these two reactants. There are two little chemicals here that are going to react together. They're reactants, and they're in this pink solvent or pink liquid. They react and they form this little blob here, which is the product. So that blob is the system. The pink liquid is the surroundings where it happens in. This pink liquid is not part of the system. It is not part of the system. The blob is the system. So when we're looking at it, it's very important to know what is a system. And that can change. So let's look at a different example of how that can change. Now, we can also look at that whole thing, the whole beaker, as the system, as being part of the system. And then the outside air, we might consider the surroundings. So it is also important to know what we define as the system and what we define as the surroundings. In this case, the surroundings is the room, and it's not part of your system. Usually when we talk about the system and surroundings, the system are the reactants in forming the product. The surrounding is in the immediate surroundings of where it is. Let's look at endothermic and exothermic reactions. Endothermic is where heat goes into the system. So you need to put heat into the system from the surroundings. So the surroundings will supply heat for the system. And now the surroundings also in this case could be the room as well. So it's not just the beaker, the pink liquid, but it's the room and everywhere else. So the surroundings will supply heat to the system. That would be endothermic. Endo. Into. Heat goes into or endo the system. Here the surroundings will be cold because heat will leave and go into. So heat, once heat leaves the surroundings and goes into the systems, the surroundings will be cold, and you will notice it in an endothermic reaction. You'll be holding this beaker and you mix these two things together and all of a sudden the beaker is very cold. That's endothermic. Okay, let's look at a example here. Here's this chap. He works out and he sweats, and there's a lot of sweat there. So sweating, your body is the surroundings and your sweat is the system. So in that case, heat will go into from the system. Heat will go from the surroundings into the system. Your skin is the surroundings, your sweat is the system. Heat goes into the sweat. The sweat grabs that heat from your skin. Your sweat now has that heat from your body. Then it evaporates. That evaporation will take the heat away. Now you feel cooler. You're much happier. So as your sweat is a system, it's endothermic because it will take that heat from your skin, the surroundings, and it will leave. Let's look at an exothermic example. An exothermic, the heat will exit the system. The surroundings are not part of the system. The heat will exit the system to the surroundings. So heat leaves the system, enters the surrounding. Now you will feel when you have an exothermic reaction, that heat leaving the system. If the beaker is the surroundings, the beaker will be very hot. Now let's look at the same thing. Now your book will describe exothermic reactions as sweating as well because it takes your body as being the system. And the whole body is a system. Your heat will leave the sweat. With the sweat, your air is the surrounding. So it goes from high heat, your body, to the surroundings. Your body is the system. The sweat, your skin, that's all the system. It takes the heat in your sweat and leaves it to the surroundings. From hot to low, the surroundings would be the air around it. In this case, sweating is exothermic because it leaves your body, your system, and goes into the surroundings.
Let's look at a system versus surroundings. This is important when we look at thermochemistry because we need to know what is a system and what is a surrounding, what is going to give heat, what is going to take heat away, etc. Now the system is defined as the set of molecules that are reacting or changing. So it's the set of molecules, that's what's reacting. So you might have a beaker And inside that beaker, you'll have the set of molecules. That's the system. The surroundings are everything around the molecules that are reacting or changing. So if we have the same beaker, here's a system. The surroundings will be the solvent in the beaker in this example. What is an endothermic process? So endo meaning entering. You can think of it that way. If you enter heat process. It's a chemical reaction in which energy is transferred from the surroundings to the system. So it enters the system. Entering the system. So heat leave the surroundings and go into the system. And exciting, heat exciting the system. A chemical reaction during which the energy is transferred from the system to the surroundings. So if we have the same thing here, here's the system. It exits and goes to the surroundings. So that's the heat in this case will exit the system and go to the surroundings. Now, what are units for energy? Units, of course, are very important. We need to keep our units straight. The units tell us what exactly we're working with. Well, the joule is a unit for energy. That's the main unit, big J, often is called. I had a teacher, algebra teacher, named Mr. Joule, and he had a lot of energy. We used to get him off topic all the time, just brought up guns or hunting, and he'd go off for the whole period talking about that. Mr. Joule, a lot of energy. Joule unit energy. So that would be J. Now, a calorie. Calorie is another unit of energy. 1 calorie is the amount of energy needed to raise 1 gram of water by 1 degree centigrade. So a gram is very small. And a calorie is that energy needed to take that little drop of water and raise it 1 degree Celsius. That's what a calorie is. That's the heat needed to raise 1 gram of water. We take a little gram of water. How much energy do we need to raise it 1 degree Celsius? That's 1 calorie. Now this notice a little c here. That is not the same as a food calorie that we see on the back of labels and that we count all the time. That food calorie is called a kilocalorie, and it's a big C. That's the food calorie. That's the ones that we see at the back of those labels. It's the ones we count. A food calorie is actually 1,000 times bigger than a normal little calorie. So what are the conversions? We need to know what a joule, how many calories are in a joule, and vice versa. Well, there are 4.18 joules in 1 calorie. Notice the little calorie. That's in the little calorie. Now, there are 1,000 little calories in a big calorie. So in a food calorie, 1,000 calories equals a kilocalorie. So when you eat something that has 10 calories in it, you're actually eating 10,000 small calories. Sounds pretty scary, but it's not that scary, so relax. And if we look at nutrition facts here, this is from a food label. So these calories, again, big C, those are food calories. There are 200 food calories. So 200 food calories would mean 200,000 little calories. So you can scare people by saying, hey, you know what? You just ate 200,000 calories. They will freak out and run away. You will be correct. You will not be lying, so you just won't be as specific as saying those are food calories. Okay, so this, when you see calories, that's energy. That's energy, which is actually kind of interesting. And what do you need for energy? You need calories, because that's what's burned. When you are burning, when you're running or jumping or just standing there or sleeping, your body needs energy. And where do they get it? They get it from calories, which will be deposited usually as fat, or it might be burned directly as energy.